Hello. In this video, I wanted to talk about birthday paradox. Um, so here's the problem. How many people do you think you have to have in a room before you can find two people who share the same birthday? So try to estimate a number maybe that might represent. Okay, at this point, you're likely to have two people who have same birthday or not. If you're a typical person, uh, maybe with a Facebook account, maybe you have friends somewhere between 100 to 200 people, maybe more, maybe less. You might know someone who shared the same birthday as you, maybe not. You might expect, well, okay, there's 365 days in a year. For somebody to share birthday with you, maybe you need to have about half of that amount. Maybe 365, so 180, 182, 183, somewhere around that number. It turns out that the actual number that you need to get 50% chance to get a birthday in common is a lot smaller than you expect. Before we get to the number, let's figure out how to compute something like this. Okay. So usually if we're meeting in person, we'll do this in a classroom and maybe we'll get it, maybe we won't. Let's actually compute how to get this. So just to simplify the process a little bit, we're gonna do it with birth month first, and then you can compute how many people it would take to share a birthday later. So, okay, if there's only one person in the room, then there's no way to have two people with the same birth month. So the first interesting case is when you have two people in the room. The second person who walks into the room, if the chance of them sharing the same birth month as the first person is 1 in 12. So the chances that they don't share the same month is 11 out of 12. And the reason why we're focusing on the opposite probability, that it turns out that this part is easier to compute than probability that somebody shares a birth month, as you might see in a second. So if there's two people, the probability that they have different birth months is 11 out of 12. And then the probability that they share the same birth month would be 1 minus that. It's the opposite probability, which is 1 in 12. The probability that three people have different birth months. So for this, it's easy to think in steps. So the first person will have his own birth month, and he can't share it with anybody else because there's only one person. The second person who walks in, because the first person took 1 month away, the second person, the probability that it doesn't double up is going to be 11 out of 12. And then, so now 2 months are taken up by the first and the second person in the room. The probability that the third person who walks into the room that does not share that same birth month is 10 out of 12 because there's 10 months left that the first two people did not take away. So that is the probability that three people did not have different birth months. Maybe this simplifies a little bit. Let me use my calculator here. Okay. So they both share a common factor of 2. So that would be the probability that 3 people have all different birth month. The probability that at least 2 people share birth month is 1 minus that. So 17 out of 72. Okay, so I hope you get the pattern on how to compute this. So for the next person, you just kind of continue the pattern. So for the 4th person, there's 9 out of 12 chance that you don't share a birth month, and then you keep continuing until you get a probability that's less than half. So maybe we could just do this right now. So with 3 people, it's 55 out of 72. And that's about 76% chance. So if I take that and multiply by the 4th person, so fraction of 9 over 12, it's still 57%. So that's not quite beyond 50% yet. So the 5th person to walk into a room, there's probability 8 out of 12 being distinct from all the other people. And at this point, the chances of them all being different with the 5 people in the room is slightly more than 38%. So the probability, this is the probability that they have different birthdays. So probability that at least 2 of those people share the same birth month is 1 minus that, which is 61.805 and so on percent. So that would be the first time the probability that somebody shares the same birth month in a room will be over 50%. Okay, so I hope the pattern made sense. Now I want you to try with birthdays. So the first person, let's just ignore people with leap year birthdays. So the first person has probability 1 of being different, right? Because of all the birthdays available. The second person is going to have probability 364 and 365 to be different from the first person. And then so on. Keep multiplying until your calculator says this is the number below 50%. And that's the first time where the probability that they share birthday is going to be over 50%. So I want you to try to pause the video and see if you can compute this and see how long it takes until people start sharing birthdays with more than 50% chance. And it's probably a lot sooner than you expect. You will not have to do this 180 times. So try it out. Is this what you expected? Or was it surprising to you? Okay, so that's the birthday paradox. There isn't anything really wrong logically here, but it's kind of difficult to like have the right gut feelings. People are really bad at um, having the right gut instinct with probabilities. So I thought this is an interesting problem. Um, let's step away from probability a little bit and talk about some commonality that people might have just based on logic. So birthday paradox is um, probabilistic argument, but sometimes you could have counting argument that kind of proves that somebody has to have the same birthdays or similar, some commonalities. And that's called pigeonhole principle. So here's the idea. It's very simple. If you have n things and you put it in n different categories, and if the number of categories is less than the number of things you're splitting, then at least one category will have to contain multiple things. So that might have been a little bit too abstract. So let's attach concrete numbers to it. So the reason why this is called pigeonhole principle is because you might see pigeons inside of pigeonholes, right? So let's say you know that there's 11 pigeons, and then they're all hiding inside of pigeonholes. And let's say there's 7 different pigeonholes. So if there's 11 things divided into 7 little spaces, then you don't actually have to go out and look into each hole to know that there's got to be at least one hole with multiple pigeons in it, right? Because if there's at most one pigeon in each hole, then you can't have more than 7 pigeons in there. So just by knowing that you have more things to divide up between categories that are less than that number, then you know that you have to double up somewhere. You could be a little bit more general with this idea. So if you have n things, that divides into n different categories, and n happens to be bigger than k times m, then at least one category will have to have more than k things. So for example, if you had a group of 50 people and you were looking at 12 different birth months, 12 goes into 50 more than 4 times, right? So 12 times 4 is 48, which is smaller than 50. So that means that there's at least one birth month where 5 or more people will share the same birth month. 5 because that's one more than the 4. Right? Because if there was no month that was shared by 5 or more, then maximum you can have in common is 4 people, and 4 people among 12 different months is only 48. So that doesn't account for all the people that's there. So I hope that made sense. Try out if you can work that out into the following 2 sections. You might think that's a really simple observation, this pigeonhole principle, but it's actually a lot more powerful than you might imagine. So here's a exercise. Okay, so here's what I can prove without doing too much research. Can we guarantee that there are at least 2 people in the world who was born in the same second? Like in your birth certificate, I think they record the hour and the minutes of the day where you're born, but they don't record the second, birth second. But this is not something you can actually check by research. But even then, you can guarantee beyond the shadow of the doubt that this has to happen using pigeonhole principle. So let's see how this might be done. So the first thing to do is to check what the world population is. And I just looked it up. It's over 7.78 billion people. It's actually more than that. I kind of rounded down to hundreds of thousands of people. Okay, so if you have the world population, so there's that many people, that's a lot of people. And then the next thing I looked up was who was the oldest person alive. So the oldest person alive was 117 years and 116 days old, currently. So that's the oldest person who's alive today. So let's count how many different seconds each of these people could be born in. So if you kind of divide up the oldest possible birth second from all the possible seconds that we have, well, converting this into how many days they are. So in 117 years, then there's 365 and a quarter days per year, quarter because of leap days. And he's 116 days beyond that, live beyond that. So that's about 428, 150.25 days. Let's just kind of round up to the next day. So 42,851 days. Okay. In that many days, there's 24 hours in a day, 16 minutes in an hour, and then 60 seconds every minute. So if you multiply all of these things, these are how many seconds they are between now and when the oldest person alive was born. Okay, so think of this as the number of categories. That's your M in the pigeonhole principle. And this is the number of people that we're dividing up into this many categories. Okay, so if we have to count how many times this goes into the world population. So if you take a ratio, you'll get a number something like 2.101 and so on. This means more than twice the number of seconds goes into the number of people. So pigeonhole principle guarantees that there's at least one birth second that was shared by at least 3 people because it's strictly more than 2. So 3 people have to share the same birth second. And we were able to compute that even without looking into birth certificates, right? So it's actually a really powerful idea. Using the same idea, you can prove that in New York City, there's at least a handful of people who share the exact same number of hair on their head, which is a entertaining computation to do. Anyways, I hope you found that interesting. I'll see you guys Friday.